Welcome to Wireless Future. This is episode number 26, and my name is Erik Larsson. I'm here as always with my colleague Emil Björnsson. Hello, Emil. How are you today?
I'm great. So 26 episodes, that's amazing.
That's quite amazing indeed. So when did we actually start this off? It's more than a year. I think it's almost a year and a half ago.
Yeah.
Wow.
So we made some test recordings almost 1.5 years ago before we started actually releasing things.
I think we did indeed. To our audience here, this podcast, indeed, it started almost, I think, really as an experiment. And then after the first recording, we simply couldn't stop. So, in any case, great to be in the recording studio again. And the discussion that we had planned for today is on the topic of network slicing.
Yes.
Before we kick that off, I'd like to revisit a comment that we got on the YouTube channel. So from time to time we get comments, which we appreciate a lot. In fact, I find it rather fun to engage when the audience engages with us and when we have a chance to engage with the audience. And this time there was in fact, a couple of comments that were very well articulated, and I felt like we should probably address them at some point. So why don't we start off with that? And the comments relate to the last episode, I think, 25, where we talked about modeling. Yes. And so here are the comments. Number one, with respect to the question about modeling errors in papers, then one thing we didn't mention but maybe should have is the block fading assumption, which is to say that the channel stays constant over some certain chunk of time and bandwidth. And the commenter here states that, well, although this model is useful, certainly one shouldn't forget that even with modest mobility and delay spread, the channel coefficients on the OFDM time frequency grid will vary substantially from one subcarrier to the next, and also over time, obviously. So that algorithms designed based on the block fading assumption don't work well in practice. And a specific example of that is channel estimation, of course. And this is certainly a very good point. Obviously, the channel response will vary from a subcarrier to the next and from one OFDM symbol to the next and so forth. Now, this block fading model is, I think it's fair to say, an immensely useful tool for capacity analysis and predictions, and for system optimization. So the assumption there is that we define a coherence block or coherence interval over which the channel remains substantially static. And inherent in that assumption is that we have a means for compensating for these variations from one subcarrier to the next, right? So that we sample the frequency response often enough in the time domain and in the frequency domain to make this interpolation possible. That, of course, shouldn't be conflated with or confused with the use of a block fading assumption for algorithm design for channel estimation, for example. Once we build actual algorithms that estimate a channel and perform the precoding and so forth, then we have to take these, we have to actually implement the interpolation and take into account the fact that there are variations from one subcarrier to the next. But for performance prediction, this block fading model is still a highly useful tool. What would you say, Emil? Any additional insights on this point?
No, I agree with what you were saying. And when it comes to variations in time, the only way of really improving on our channel estimates would be to send real pilots again and again. So if we are not really knowing a lot about the mobilities, we can predict things. But then over the frequency domain, there's definitely opportunities to interpolate in more advanced manners and actually utilizing that all the subcarriers are sort of created from the same physical channels, and which is typically what is done in real system, I suppose.
Right, of course. And in a way, I suspect there's a little risk here that some students of, let's say, applied information theory or if you read the typical, let's say, massive MIMO capacity analysis paper, there's a little risk that we're brainwashing the students or readers to think that the channel is actually block fading, right? Which it isn't. All we're saying is that, well, by application of appropriate compensation algorithms for the purpose of capacity analysis, we can treat the channel as block fading, and that's it. And then, of course, in the real practical implementation, you'd have to implement some interpolation across frequency and maybe across time. Yeah. So that's a good point. This is a second point made, I think, by the same commenter on YouTube, stating that I was somehow expecting that you would mention the 3GPP 38.901 channel model, which is widely used in industry. And this is definitely not useful for pen and paper analysis, but it is the gold standard against which to evaluate algorithms that actually go into products. And that if more academic researchers would use this model for evaluation, it might be easier for industry to adopt their algorithms. Yes, maybe. I mean, no doubt, it's highly valuable to have a gold standard common model that folks have agreed on and which bears presumably some resemblance to reality and evaluate performance against it. Even so, I think it's probably fair to say that, I mean, at least like serious, simpler academic models that are being used do capture the main physical phenomena to the first order, right? I mean, you know, we got path loss, we got shadow fading, we got Rayleigh or small scale fading, we might get like correlation of the fading and so on, and then exactly what specific detailed model is used to capture that is probably of less importance, like we discussed, was it last week? On Wireless Future 25, I think. But I definitely can see a value of, in certain circumstances, using an agreed upon model like this 3GPP 38901. I don't know whether, let's say, an increased use of that type of simulation models in academia would result in more algorithms being adopted in products and so forth. I'm not sure about that. It's possible, perhaps. But what do you think, Emil?
I think that there is an important point here is when it comes to that we should use more common models to evaluate algorithms in academia. And there is this tendency that everyone is presenting their own system model or simulation model. And then you say, my algorithm is better than yours, but I didn't compare on the same models that you were considering. So is this really a fair comparison? And if one then looks for what would be a good common model to consider in the simulations, well, then this is definitely the gold standard when it comes to industry. So from that perspective, one could have a common benchmark. Then there is, of course, this risk that we also talked about in last episode, that if you design algorithms particularly for this model, assuming that that one is the only one that will be considered, then we might be able to exploit special characteristics in that model that doesn't exist in reality.
Indeed, that's a big risk. I mean, you know, algorithm design we should be cautious not to make the algorithm design over-reliant on particular features that might appear in some model, be it the gold standard or not for performance evaluation. I mean, but the bottom line is that reality is so diverse, right? And depending on where you go and run your system or measure your channel, let's say, behavior, you might see very different things. Yeah. All right. So this is the third remark made by the same commenter on YouTube, and that concerns the discussion point we had on generative models for channel modeling. And commenter states here, I also have some doubts, but I would say that a potential advantage could be that these models can capture effects humans can't, and that they are much easier to implement than the man-made 3GPP models. Anyone who has ever tried to implement them would probably agree. So on this one, I have less intuition. Do you, Emil, have any insight?
Yeah, I've been definitely trying to read some of these documents just to create simulation environments that are maybe not compliant with the 3GPP simulation models, but are at least bearing some of its features. And those documents are incredibly complicated to follow. And I also recently attended a workshop from people at MATLAB who was describing that they have an implementation and how difficult it was to just validate that their implementation was accurate, which we can suspect it is nowadays. But it's hard to read the specs and be sure to implement the right thing because it's so complicatedly written.
Yeah, which speaks, sure. Okay, maybe we should move on. So, in any case, to reiterate, we love to engage with the audience and appreciate a lot, of course, when we get well-articulated and substantive comments like the ones here. So, to today's topic, network slicing. And I have to start off by saying that this is a topic of which I know very little, if anything, but you, Emil, know a lot more. So what we're going to do here is I'm going to ask you things relating to network slicing, and we'll discuss around that and those questions. So, so where do we start? What does this mean, network slicing, the term?
So the idea here is that you deploy one physical network infrastructure with base stations and core network and everything, and then you use it to create multiple networks in a virtual fashion so that people are accessed in different ways. So you sort of, instead of having multiple networks, you have one network that slices its resources between multiple virtual networks.
So what does this mean more concretely then? I mean, you said, I think, network equipment. What does network equipment mean? Is that like a router or a 5G base station or something else because I mean there are the base stations, right? And then there's the whole core architecture behind it,
yes,
or behind them.
So it involves all of these things. So we have what we call the access part. These are the base stations, and that could both be a base station in a cellular networks, and of course you can also think about your Wi-Fi station at home. Then you have the transport network, which is sort of connecting your base stations to the rest of the world. So there could be fiber cables, other things that are connecting you to your telecom operator's core network, which is then the one that is connected to the internet and to different service providers like a Netflix server or something like that.
Okay, so the base stations kind of share their resources among various different tasks, and each task is associated with like a virtual network. Is that a fair way of paraphrasing what the slicing means?
Yes, and I think one way of thinking about it is also to go back historically. We have been deploying a lot of different physical networks, one for TV broadcasting, one to send out FM radio so you can listen to music in your car, and one for sort of telephony, for example, and the cellular networks. And then we have seen this convergence where we start to use more and more things through the cellular networks. So all of the services are running through that network. And then that means that we could eventually perhaps turn off the other physical networks and only have one physical network where all the services are floating through that one.
I see. So you're saying like using this one piece of infrastructure, of physical infrastructure, to provide a variety of different services that traditionally had been their own networks with their own independently operating like base stations and so forth.
Yeah, and think about it a bit like the transport networks are vehicles, that we don't have different roads for different types of vehicles. We have, of course, a few different things. We have roads for vehicles that you can drive, and then you have trains. But we are sort of, we don't necessarily need to have a lot of different physical networks, even if we have different services.
Mm-hmm. Yeah. So traditionally, I mean, I thought for wireless networks, they have been, or at least traditionally, or at least, well, let's say in the last, 20 years maybe, they've been packet switched, right, based on TCP/IP type of architectures and designed to just deliver packets irrespective of the actual contents of these packets. So now this slicing, would that mean that we leave this paradigm in the future, or how is the, say, concept of packet switch data related to slicing to the extent it is?
So there are a few different ways of thinking about it. The simplest thing would be that different telecom operators are just sharing the same base station. For example, in the countryside, maybe there's no need to deploy 3 different base stations covering the same area. But I think more generally, one should think about that we might need different services. And just to take a very different but telling example, the post office services, you can send your mail by just putting it in the mailbox, and then you know that it will be delivered according to their best effort. You don't know exactly when it will be arriving, but if you don't care so much, it will be delivered. But then you could pay to get your envelope picked up at your door and left at the receiver's door within a certain time frame, or you can pay extra to have security so they check the ID. So there are different types of delivery services for different type of packets, and think about then that the same thing would apply for different types of data packets. So it could still be packet switched over the network, but there would be different parallel services delivered by the same entity.
So you're saying like that every time you'd ship off a packet, you'd also tell the network or the infrastructure then how urgent this packet is, and whether it would have to be delivered with something like the analog of registered mail or urgent FedEx Express. Exactly. Or something. Yeah.
Yeah. So if we have we often talking about that we would like to have a quality of service in our networks, and many times when people are just saying the word quality of service without defining it, it means we would like to deliver things with a certain data rate, certain bits per second, and that is sort of the only important metric. But then nowadays we are talking about a large number of different so-called KPIs, key performance indicators, and these are of course data rates, but also things like latency, reliability, availability of the service, and energy efficiency, security, and different things. So one can see that different devices require different mixes of these performance indicators being good in different ways, and also the same device might, for different types of packets, depending on their content, need a different mix of performance indicators.
So back to the concept of slicing. I mean, so you're explaining that slicing means that we have some piece of physical infrastructure. It could be like a base station tower. And then we like partition its resources right into, and thereby create like multiple virtual networks that exist in parallel. So what is the real point of doing this? I mean, why don't we build one single network from the outset, which is good at everything that we want to do?
Yeah, that's a good point indeed. And it has to do with this large number of different performance indicators. So when you have multiple ways of measuring performance, there will be some kind of contradiction between them. So one of our colleagues at Ericsson once told me that, a duck could be the optimal animal because it can fly, it can swim, it can walk, but you don't typically view a duck as being the best animal because it's not very quick at running or very good at flying. So you would like essentially your network to be more like a jaguar that is running very quickly when it needs to do that, or it should be sort of some other kind of animal that is good at swimming when that is needed, so to say. But you don't want to have these multiple parallel physical networks. You would like the network at itself to reconfigure itself so that it behaves in these different manners depending on what service you like to deliver for a particular customer.
I see. So is there a connection here? I mean, there's another term that I wasn't sure about: network function virtualization. Is there a connection to that here, or is it the same thing really as network slicing?
So this is one of the enablers of being able to have this kind of flexibility of changing your behavior depending on what customers are asking for. And this also together with what we call Cloud RAN, Cloud Radio Access Networks. So the core idea is that instead of having the base station that have its own computing resources next to it that is designed with dedicated hardware to only being able to do one task but do it very well, then you are instead virtualizing all of the computations in a general purpose kind of data centers that could still be close to the base station, but you sort of break down the kind of computational tasks that needs to be done in order to implement your network into different pieces that you can run at different types of hardware. And that gives you then the flexibility of saying that, well, if we have a lot of traffic of this kind for the moment, we could let a large portion of our computational resources carry out the network functions that are needed to enable that service. And then if we are switching that we need a lot of other service, we can virtualize that. So we are essentially then making sure that we can reconfigure what kind of hardware resource we're having, because we are not limited by exact ASIC implementation of something, but we are virtualizing things as much as possible, and we can scale different services up and down. We are also essentially pooling the resources between neighboring base stations, usually in this cloud run infrastructure, so that they shouldn't be in a situation where one have a lot of computational resources that no one else can use. You're sharing.
Yeah, so is it a little bit like, so you have all this infrastructure and then it's reconfigurable, so that if somebody buys a megahertz of spectrum license somewhere, then you just instruct the network that, look, I have this megahertz of spectrum, and could you please just reconfigure yourself and start up a little virtual network in this spectrum slice, and I want these and these KPIs and these and those, say, performance requirements, and then the network would just reconfigure itself and offer that service and that band that you had bought.
Yes, that is one possibility. So I think we talked briefly in episode 24 about private 5G networks. So if you would get your own license to use some spectrum in your building, your enterprise area, then instead of deploying all the network infrastructure yourself, you could essentially contact an existing 5G network around you and say, look, can I piggyback on your hardware? And you can virtualize my network, even if you don't have your own spectrum license.
No, I'm just trying to understand the use cases here, but the one that I sketched seems to be like a legit one then, right? That you have bought, say, a license for some spectrum, which could be intended for, as you suggested, use for a private 5G network in a building or some limited geographical area, and then you just tell the physical infrastructure that, look, reconfigure yourself to offer now this specific service in the spectrum that I bought.
Yeah, and this is shaking up a lot of the business models. We have been used to wanting telecom operators to compete. So we might have 3-4 different physical networks in every country, and then there might be some additional virtual operators that are using their networks. So that's also like one starting point of this. But then if the base station hardware are able to transmit the signals for all of these or multiple of these operators and networks, why not use the same physical hardware and then just separate things in software? And then in the same way, if you have your own 20 megahertz for your local area, why not let the base station that is able to handle the same spectrum deal with that for you?
Right, I see. So maybe getting back to like different terminology that I never been sure about. Then we did talk about network slicing as like the main term. We talked about network function virtualization. There's another term which pops up now and then, I think, in this context, and that is orchestration, network orchestration. What does this really mean?
Yeah, this is a popular term that a lot of people who are in this business are using all the time without really defining it, just viewing it as everyone is knowing already what it means. But I would say that it means that when you have this possibility of reconfiguring everything in the software, you need to have this extra layer that we call the orchestration layer that is controlling how should we split up, how should we slice our resources for the moment, and what are the needs, and if you now can virtualize the computation, where should you put computation and things like this. So it's really a way of controlling it. And if you are then signing specific so-called service level agreement with some enterprise that would like to buy a certain slice of you, for example, in a local area like that, then it will contain some constraints on what service they are paying for. And then this orchestration layer should be sure to all the time deliver the service that you need. Then exactly how you do it, what computational resources are utilized, that might not be specified. Then you have all the flexibility in the world, but you need this layer to control the whole thing, to orchestrate it.
Yeah, so orchestration, in short, I mean, really that means some kind of controller that allocates computational and other resources across all the infrastructure, and make sure that things just fall in place and work together. So I don't know, maybe we're going around the topic a little bit here, but we did talk about applications of network slices or network slicing, and one was, I think, what I somewhat perhaps naively suggested, that you get your hands on a license for Spectrum and then you want to start off some private little network there, and rather than buying your own base stations, you could then just rely on existing towers and infrastructure and just ask them to reconfigure and offer you some particular kind of service in this little band that you bought. What other, if any, I mean, applications are there out there of slicing?
So there is a large flexibility and designing slices in the way you like. So when people were talking about 5G and how to develop it, there were particular three use cases that one was talking about all the time. It was enhanced mobile broadband, which is essentially this first slice that we already have seen. And then there was ultra reliable low latency communication, particularly then for some services that requires not maybe so high data rates, but it should be super reliable and the latency should be below. And then there is the massive Internet of Things kind of devices that should be very energy efficient, for example. And we have already seen this narrowband IoT kind of versions of 4G, for example. So that would be essentially one such early slice implementation. But you can think about other configurations. So right now, if you look at websites for some of the companies in this business area, they are talking about different types of IoT, from critical IoT to massive IoT. So essentially, you can choose whatever service requirements that you want and try to get someone to deliver that for you.
So when these services are defined, like for example, I think you suggested earlier that one could set up a small private 5G network on some property or even in the building, and use network slicing to accomplish that. So rather than buying your own access points or base stations, you just rely on infrastructure which is already available out there. That sounds to me like a solution which is like geographically local or confined, right? To the property that you own, or the at least the area where your license is valid. But could network slicing also be used on a larger geographical scale, like over an entire country or even a continent? Or would there be some use cases for that?
Yes. So if you do it in a local area, then if you require very specific type of requirements and things, then you can definitely deploy some extra physical infrastructure to enable that your slice is possible. If you do it over a larger scale, then that could be, for example, if you are going to use the 5G networks for connected vehicles, for example, then you will need it to work over a larger scale. And then it might become more of a static kind of slice that is enabling 5G connected vehicles to talk to each other or get information from the network. So you might have less flexibility to change things on the local scale if it should be the same over a large geographical area. But yes, I think one of the core thing here is that we are believing that the 5G networks will be so capable that for a single user, we just have so much more capabilities than the single user will request. So that's why we can sort of afford reconfiguring ourselves and maybe be less efficient, but still deliver services.
Yeah, so I mean, I would imagine that all this slicing also requires a lot of coordination among the infrastructure, it's one thing if you have a single like base station or access point and you decide to slice your spectrum and offer different kinds of services in each slice, maybe different customers and different operators even that own the or provide the services. But now if you do this like over a large area or even nationwide, I'd imagine that would require a lot of coordination among or within the infrastructure. And also, it seems to me that at some point, the slicing won't be meaningful any longer. I mean, there's got to be a cost of slicing, right? And the more you slice, the thinner slices that you like slice up, the less each slice will be able to offer, and the higher will be the cost of all this coordination and orchestration. Is that so? And do you have any like feeling for when do we reach that point? Here, is this really efficient in the end, I mean?
So you're definitely right that if there would be one particular performance indicator that is the most important one, then starting to slice your network and optimize other metrics, of course, in terms of that original metric, it will be worse. So you are sacrificing something, particularly if you have static slices, you are sacrificing flexibility. So there is a hope that you can change that back and forth to gain something back by being flexible, increase or decrease the sizes of slices depending on the needs. But then I think one should also bear in mind that the physical infrastructure doesn't need to be a fixed amount of it. So when you add new slices and you realize that we can't really deliver these services, or we start to get unreliability issues, well, then we might have to deploy new infrastructure to be able to add this slice to our network.
Yeah, I see. Okay. So one thing I'd like to return to is a point you made earlier that with slicing, you could offer like different packets in the network, different treatment, right? So that some packets could carry a stamp that they are urgent, and some packets could carry a stamp that they aren't so urgent, but maybe they are, I don't know, big or need to be conveyed with some particular privacy or security requirements. So doesn't this like fundamentally contradict a bit there is this, in the European Union, there is this net neutrality directive, which to my understanding states that when you provide a broadband or internet service, then you can't discriminate between different types of traffic. You've got to treat all types of traffic equally. Isn't there like there seems to be a bit of an apparent contradiction there? Is that something you could maybe comment on?
Yeah, so I think this is an important point to bring up, and one of the successes of the internet have also been what we call the end-to-end principle, where it's about delivering package without caring about their content and try to do that in a best effort manner. And we often hear that is the reason why it works, that we didn't try to put too many restrictions on things. But if you look at these net neutrality laws, then what they are saying is that we should deliver basic services to everyone in a manner that is enough for everyday use cases, and we shouldn't restrict people too much based on how much they can pay for the services, but everyone should have access to the internet. But there is still an possibility that is also allowed to charge extra for premium services. Or specialized services for different situations, and this is really what this is about. To still have conventional internet access, maybe that is the mobile broadband, but then have these extra services that enterprises could buy. And so in the short term, this is not a problem when it comes to net neutrality. Then one can definitely see a threat in the long run if these premium services start to be something that everyone wants. So suppose in a few years from now people will start to use some augmented reality glasses, and in the beginning you have to pay a lot for the glasses and for the special connectivity, but then progressively it becomes mainstream. Everyone wants it, and if you still then needs to pay for a specialized service for it, then the network neutrality might be more of an issue, that only some people have access to this new brand world of augmented reality and not everyone else. So that's definitely a long-term issue to keep your eye on.
That's the distinction, yeah. Okay. Is there a connection to spectrum sharing here? I mean, because it seems to me the network slicing is mainly about using or sharing infrastructure, right, for multiple purposes, or at least multiple like virtual networks. Is there any connection to spectrum sharing at all here, or is that an entirely like separate thing?
Are you thinking about it like a cognitive radio?
Yeah, in that sense. I mean, that the term was used when, say, cognitive radio was hot, maybe 10, 15, I don't know, years ago, even longer.
I think it is primarily the idea that someone owns the spectrum and is the only one allowed to utilize it. But then what infrastructure is used to generate the signals, that is then what is determined in different manners.
So the slicing, I mean, what you're saying is that the network slicing is really mainly about how to use, how to split the infrastructure functionality and permit service of the different virtual networks, but whoever owns a piece of spectrum just owns it. And
yes, I think that is still, for the time being, the enabler of being able to deliver services with some quality of service constraints that you can guarantee.
Right. Yeah. Okay. That's been interesting. And I don't know, is there anything else that you feel is important to convey here that we haven't covered? Emil, a question I'm sitting on is like, what are the research problems here, right? I mean, especially for someone like, well, you've been deep into MIMO for many years, and you know, for someone like, let's say, us, who have been interested in mainly perhaps physical and MAC layer aspects of wireless, but in any case, what are the research problems really here, to the extent there are any in that domain? Do you have any like insights on that, or is network slicing mainly a matter of making the electronics flexible enough and the software flexible enough to enable this splitting of physical resources into several parallel networks?
So I think that a large portion of this technology will not be standardized. We usually standardize this kind of skeleton of what kind of signals to pass around to make all the devices being able to talk to each other. But then they can still reconfigure themselves, and now they should reconfigure a lot of the features and select how to behave from some maybe standardized list. So a lot of the research here would be connected to how to design these orchestration layers and how to design other types of resource allocation features. And a buzzword that is often used is end-to-end network slicing, where you want to really create parallel virtual networks with the access being different, and you're using the same transport layers, but you are sort of creating virtual different pipes within it, and the core networks is split it up, and maybe some pieces of this have some special constraints, so one enterprise don't want their data to leave them, then they have a special server that only they are using, and to solve different kinds of resource allocation problems related to orchestration and figuring out how should we split things up for the moment to deliver on the service constraints that we're having.
Right, but when you say split things up, you mean really like within the, say, infrastructure. I mean, be the base station, there'll be certain hardware that does computations, right? I mean, the span from the physical layer up to, well, a few layers up, and how to really split them and share them across these different networks. I think that you wouldn't go deeper than that. I mean, it's like if you have a MIMO array, say with 100 antennas or something, it's not like you would suddenly split and say, well, the first 10 antennas go to the first network and the next 10 antennas goes to the second virtual network and so on. Or is that even a meaningful line of thought, or is this mainly a matter of like organizing the software and the computations and the scheduling of all the data processing that has to go into the base station?
I think you are right. The physical layer will be operating the usual way, but when solving scheduling and resource allocation problems, we will now have many slices with different objectives and constraints, which makes them much more complicated to solve. So that is a big research challenge. So it would more be, okay, you have all this network function needs to be computed. They have different latency requirements. At what server should we place them? And in which order should we compute things so that we can make sure that everything is being computed and satisfy their service requirements. Then one can definitely bring in general efficiency concerns, like things when it comes to energy efficiency in low traffic situations, when you have an abundance of computation resources. How should we pool things together so we can turn off things, or we don't need to use certain transmode cables and things like that.
Right. And for the purpose of saving energy, I suppose, I mean, it'd be highly useful to turn off things that you don't need for the moment. And it seems like an interesting problem to address how that would interplay with this orchestration. And in the end, I mean, it all comes down to deciding which little component or piece of hardware and maybe software does what at what point in time, right?
Yeah, so it's a bit like solving conventional resource allocation problem, but with a lot of new constraints, and maybe then also services with different metrics, so we don't have just one metric, it's become some kind of multi-objective optimization problems.
Right. Wow. All right. I think it might be time to close up, or
I think I have one more thing that we could talk about, and this is really what is that is driving this kind of trend here. Why are we talking about network slicing now? Because I think one symptom of this whole thing is that when people start to get in first 5G phones, I could see people in TV commentators saying, yeah, now there is a new iPhone 5G enabled, but this isn't really 5G. This is just, a little bit faster perhaps, but 5G is really about this ultra reliability or the massive IoT kind of things. And I think this is a symptom of the fact that there have been a lot of marketing efforts around that 5G will support network slicing. And the reason for that, I believe, is that this is sort of a stagnating market economically. People have their mobile phone, they have the subscriptions, they don't want to pay more every month, but they want to have a progressively better service. And when people are paying for new things, it's all often this over-the-top services like, people are home in the pandemic, so let's get both a Netflix and a Disney Plus and an HBO subscription. So you're paying for the data that is delivered certain services, but not to the telecom operators. So what can the telecom operators do in order to make more money? Well, create new services. And why would then anyone would like to pay for those new services? Well, I think that is two main reasons. One is that businesses like to outsource things that are not the core business. So instead of having expertise that is having their own Wi-Fi network or something like that on their premises, if they can just buy that services from the nearby 5G network and maybe put up some extra equipment inside the building, well, then that would be a good way of not having to control your own network, but still sign an agreement where you are delivered the service you have today and potentially more. And then there will be very demanding use cases. It could be like a stadium, it could be a factory that should be automated, so you want to get rid of cabling and connect everything wirelessly, or it could be an airport where you have this mix of services. So take the stadium as an example. You might have a lot of cameras in the future that is filming everything from different angles. And then you have a lot of like 100,000 people in the audience who might want to watch some extra information in their phones or in their augmented reality glasses. And then it's incredibly important that the camera is functional all the time, because it's their information that will be spread to other places. So they might need ultra high reliability. But then for different users, you might be able to sacrifice them or deliver things in a more best effort way there. So there seems to be convincing cases for this actually happening economically, and company like Ericsson are saying that it might be a $700 billion market for this kind of network slicing extra services in 2030. So it's really,
wow, that's a lot.
Driven
I mean,
here.
700 billion worldwide. If you divide by 7 billion people, that's like $100, right? So,
this is a development that is really the reason why 5G is sometimes said to be about enterprises. It's not only about enterprises, consumers will also want this, but there is this hope that 5G will really create new revenue streams from enterprises.
So it seems then, I mean, in light of what you just said, that network slicing, although it obviously requires the development of a lot of new technology, but it's really in a way driven by new business models. For example, this possibility of, possibility of, again, buying a piece of spectrum and then just telling some infrastructure provider that please set up a network in this slice of spectrum and run it for me.
Yeah, exactly. And then when you are signing the agreement with them, then you might be using partially your existing network infrastructure. Partially, you might realize, okay, I need to put up some indoor base stations in their premises, or they are very protective on their data, so I need to have a cloud computing service server that is inside their premises as well. But you sort of still piggyback on some of the existing infrastructure, and then you're saving costs in different manners.
Right. So it's like the contract might specify some KPIs, like, well, this is the data rate and coverage and reliability and so forth that I want. And then, well, to get this, you can rely on this and that tower, which is out here, but you'll also have to install a couple of small base stations on your property yourself. And we are going to make sure that all this happens and orchestrate all these pieces of equipment together. And there's nothing really you need to worry about more than paying the bill.
Yeah, exactly. That is the hope.
Wow. All right. Yeah. Great. Emil, thanks a lot. It's been a very educational discussion, I think, and I learned a lot. And maybe it's time to close up here. So with that...
I think we will maybe return to some of these specific use cases in the future episodes as well. So if you have some particular request, please write a comment about it, and we that will guide us also in maybe future guests that we can invite to discuss on some of these topics.
Absolutely. So with that, bye-bye, Emil, and bye-bye, everyone.
Bye-bye. Thank you.